Okay, so what we're going to do now is we're going to talk about an example, a detailed example that shows how Java 8 streams work. And we'll be focusing on sequential streams in the context of an example called SearchStreamGang. You can download the code for SearchStreamGang here. This example is kind of cool because it shows off lots of different ways of doing streams, sequential streams, parallel streams, completable futures, RX Java. It's kind of a Rosetta Stone of different ways of doing interesting stuff that all do the same thing. We're going to focus right now just on the sequential version. And as you can see, if you look at the timing results, this is the slowest version, but that's okay. It's a place to start, and we'll get a chance to learn about how all the features work. And then when we go to do the parallel version, it should run pretty fast. We're going to show the processStream and processInput methods. And this example is a lot more interesting than the simple SearchStream program that we looked at before. And so it'll be the starting point for a lot of other cool stuff. Okay, so what does this program do? So this is a revision of an earlier version. If you're ever curious to see how Java 7 style programming works, take a look at SearchTaskGang, which use Java 7 features like executor completion service and executor service and so on. And what that version showed, which this version shows also, is the concept of embarrassingly parallel processing. So remember, that's where you have no dependencies or few dependencies, and therefore you can just scale things up almost linearly. In fact, it is linear. It's actually super linear for reasons we'll see later, where you throw more cores at the problem and it just runs faster and faster. So that's the best kind of thing. SearchStreamGang is also a more powerful revision of simple SearchStream that we looked at before. And what this does is it uses regular expressions to find phrases in the works of William Shakespeare. So if you recall what SimpleStreamGang did, it looked for an individual word in an input file, one input file, whereas this is going to find phrases, which could be entire quotes or lines or whatnot, in the complete works of William Shakespeare. So if you wanted to find a famous Shakespeare quote like, "Brevity is the soul of wit," then this program would go and search all the different parts of Shakespeare's plays and sonnets and so on, and it would find where brevity is the soul of wit occurs. And a phrase can actually match anywhere within a line. So you can have a phrase that cuts across lines. And that turns out to be a little bit complicated to implement using regular expressions, but we'll take a look and see how that works. It's pretty cool. Under the hood, there's a whole bunch of concurrency and parallelism strategies that are used in this implementation. You can see here we have about 8 of them or so. And that's actually more because there's all this RX Java stuff. And so it illustrates sequential streams, parallel splitterators, completable futures, blah, 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 blah. What this allows us to do, why do we build this framework? We allow it to be able to do apples-to-apples performance comparisons. So you can see how the different versions of concurrency and parallelism in Java work relative to other ways of doing things. And that way you can see the trade-offs, right? Which is always a good thing to be able to know. We'll cover all the concurrency and parallelism stuff after we cover the sequential stuff. So let's start off, as I like to do when I give these discussions, by visualizing how streams work. And I just happen to work better if I can sort of think in my mind what's going on, and then when I write the code, it somehow makes more sense to me. Different people work in different ways. So there's a couple of methods we're going to focus on. These are part of a class called Search with Sequential Streams, which, as the name implies, is going to do sequential searches. And there are 2 methods, processStream and processInput. And both of these have streams in them. As you can see here, the processStream method will take all the input, which are the works of Shakespeare, each play or each sonnet or whatnot, and it'll turn all that input into a stream of input. It'll then call processInput on each input source, each play, and it'll collect all that up into a list. That's what processStream does. processInput, which as you can see is called from the processStream stream, what that does is that goes ahead and takes each phrase to find. So remember, we might have some 38 or so works of Shakespeare, and we might have dozens of phrases we want to search for. So we take the phrases and we search for each phrase in each input source. And this is also a stream, and it goes ahead and searches for each of the phrases, filters out the stuff that is not found, and then makes a list of results and returns it as the result of process input. So notice we have sort of nesting of streams, which is kind of interesting. And this discussion will illustrate the aggregate operations like map and filter and collect and so on, which you'll get a chance to use in your forthcoming assignment. All right, so let's take a quick look at how this is visualized. Keep in mind, once again, this is a logical view of how the streams processing works. The physical implementation is ever so different, but it's more or less the same idea. So we start out with a list of phrases to find. This is just one piece of this. Is the process input phase. So we have an input string, which is the particular work of Shakespeare, like Hamlet or Macbeth, and we then have a list of input phrases we want to find in that string. So the stream method will convert the list of string into a sequential stream of strings. So notice it's a string-to-string mapping, but we go from a collection to a stream. So the output of stream is a stream. Surprise, surprise. That is then fed as the input into the map method, and the map is going to search for the phrase. So it's going to look in the input string and see if it can find a match of that particular phrase, one phrase at a time. And that will look for it. We'll see how that gets done. That uses the regular expression pattern matching I was talking about earlier. And the output of that is then a stream of search results, where a search result keeps track of where in that input the phrase was found, what index, what starting index the phrase was found. And it may be found multiple times, it may not be found at all. So what we get there is an output stream of search results, but not every search result is going to have anything useful in it, because sometimes we didn't find a word in a particular place. So if you look up the word, supercalifragilisticexpialidocious in the work of Shakespeare, you will not find it, right? It's not going to be there. So we'll get a search result that's empty. So we want to get rid of all the empty search results. So of course we're going to filter them, and filter will exclude everything that is empty, so it'll only let through things that are not empty. And you can see that from the method reference and the predicate negator here. So only allow stuff that's not empty. That's what that says. And so what we end up there with is a stream of non-empty search results. So you can see here we winnowed it down from everything to just a few, whatever matched, if any matched. And then we go ahead and take that as input to the collect operation. Unlike map and filter basically take their input and either transform it or allow it through or not, right? It kind of works in a swim lane, right? So you can see if you look, so far what we've seen is it kind of goes down in the swim lane, right? Each of these things, each of these behaviors works on stuff coming to it. And in fact, that's actually the way it works under the hood, because it doesn't actually go across, it actually goes down. It's pulling the stuff down. But when we get to collect, all of a sudden, we shift our focus. So whereas map and filter go sort of vertically down in their swim lanes, collect is going to cut across, and it's going to collect the results, as the name implies. So when collect is hit, remember collect is a terminal operation, and terminal operations do two things. They trigger all the other processing, and they also create a reduced result. And the reduced result here is a list that contains all the non-empty stream elements, or more specifically, all the things that came in to collect, or what will be collected together in order to form a list of search results. So that's kind of the way to think about that. We'll talk about that later when we talk about other types of reduction operations like reduce and so on. But this idea is that the intermediate operations kind of work in their swim lane, and then at the end, the reduction operations coalesce everything together. Any questions about that? You don't really have to know the details to use it, but it just helps to think about how it works. Yes? Yeah, great question. Very good question. The question is, does it work in parallel? So no, it doesn't work in parallel for this version. All that's happening is that it's sequentially processing these things through their swim lanes. But that's happening sequentially. When we go to a parallel stream, you'll see that it actually does, in fact, run in parallel. So the way to think about this, I think I see where your question is coming from. So, what's going to happen in a sequential stream is when you get to the terminal operation, then for what you're going to do is you're going to go ahead and start pulling the data through the filters. And whatever you end up with at the end is what you end up coalescing and collecting in this case. But that's not going on in parallel. That's just happening, sequentially, one at a time. But that's a good question. Kind of foreshadowing, we're talking here about sequential streams. The visual syntax here basically says all of these computations run in the same thread of control. So we draw a dash box around the whole thing, and we put a little squiggly line that says thread. That's what that means. That says there's a thread. Later, we'll talk about parallel streams. And as you can see here, the visual syntax says some of the stuff runs in one thread, like the original stream operation is a single-threaded thing. And then from that point onwards, these two chunks or substreams are going to run in parallel in different threads. This thread deals with this chunk. This thread deals with that chunk. How are the chunks created again? What's the mechanism in Java that's creating a chunk? Starts with an S. Splitterator, right, exactly. So the splitterator's splitting the input into chunks. That's then being fed to these threads, which run in the fork join pool. And then when we all get down to the bottom again, a single thread will be used to coalesce them all together. So that's kind of the, map reduce, split, apply, combine. That's kind of the paradigms of processing that Streams is implementing. And things that are well suited to divide and conquer work great with this model. But not everything works in a divide and conquer-like way, of course. All right, and we'll come back and talk about that. The key thing that you want to remember for the moment, and I'll prove it to you later when we get to the parallel streams, is the change here is absolutely minuscule. And all that's really changing is we're going from stream to parallel stream. So when you see the code, you'll see that we just changed this to parallel stream. And as long as you followed the rules and have been careful in either using totally stateless behaviors or you've protected your data from race conditions through synchronizers, etc., then moving from a sequential stream to a parallel stream is really, really simple to do. And your program just runs faster, maybe. And we'll talk about when it runs faster and when it doesn't shortly. OK, so that was the visual perspective. Now let's take a look at the code, right? We're not, this is not a course in CAD. It's not a course in model-driven engineering. So we can't just draw pictures and have code come from that. We actually have to write text. So here's what we're going to do. processStream is the portion that handles searching for phrases in a list of input strings, where each string corresponds to a work, like Hamlet or Macbeth. So that's kind of where it's happening. We have input strings to search, and we're going to process the input and collect things up into a list. So here then is the implementation. Here's the processStream method. And what it's going to do is it's going to go ahead and get input, which will be a list of character sequences. So each play, each work in Shakespeare is represented as a character sequence. A character sequence is the base interface of string. So if you use a string in Java, string implements character sequence. And there's a reason we use character sequence rather than string, and it has to do with some optimizations that you can do with character sequences that you can't do with strings when it comes to getting substrings. A subsequence is much faster than a substring, and I'll talk about that later. The results here, what we're going to get back as a result of this, will be a list of lists of search results. And I'll talk about why we have a list of lists later, and we can also talk later, I'll talk and show you how to flatten the list of lists into just a stream of search results, which could be useful at certain points in the processing phase. A search result is basically a data structure. It's a class that stores a number of times a phrase appears in an input string. So as you can see here, we have a search result, which keeps track of what thread it was processed in, the word we're searching for, the title of the play, and something else that doesn't matter right now. And then down here, we've got a bunch of methods, the most important of which is there's a result class, and we have basically an array of a list of these things, and that's what keeps track of where the word appears in the input, if it appears at all, and if it appears more than once. So we have basically a list of offsets that says, where does this thing start? Okay, so we basically have a getInput method, which is part of the framework that returns a list of character sequences. And then we take that input list and we convert it into a sequential stream, and we run this pipeline of processing operations on it. So these are the aggregate operations. This is the factory method that just turns the input list into a stream. No surprise there, that's pretty straightforward. Under the hood, the way this works, if you go and look at the code for stream in Java, it uses this stream_support.stream method, and it calls splitterator, which splits the input into chunks, and it passes in the false flag, which says run this sequentially. So we get a sequential stream that splits the input. You know, there's 38 works of Shakespeare that are worth noting, 37 plays, and a chunk of sonnets. So there's 38 strings, and this will then just basically chunk them. It actually won't chunk them up. It'll just get them all one at a time. Map is going to take that stream as input, and then it's going to call processInput on each element of the stream, in other words, on each input play, each work, and it'll then return an output stream of a search result list that's obtained by applying the processInput method reference to each input in the stream. So it's a stream of lists of search results, kind of a mouthful, and you'll see how that gets used. Then what we'll do, there's a list for each input string. So for every input string, we're going to get back a list of phrases that matched. And then we're going to take that and we're going to collect it together into another list. And that's why we end up with a list of lists. So every item in the list is the contents of what matched. And then that's what gets returned. So processStream returns a list of search results that indicate how many times each search phrase appeared in each input string. All right, so now let's take a look at the processInput method. This is yet another stream. As you can see here, what this does is this goes ahead and will convert the list of strings it gets, which correspond to search phrases, into a stream of strings. It'll search them, it'll filter out the results, and then it'll return the results as a list. So here's what it looks like. Each of these things corresponds to a work of Shakespeare, and we get the title of the work, like Macbeth or Twelfth Night or whatnot, and then we go ahead and do a subsequence to split off the title from the work. And the reason why we're using character sequences is because subsequence is more efficient. What string does in later versions of Java, for various reasons having to do with memory management and trying to avoid memory leaks, is that substring, if you call substring, it makes a copy of what you had, which is excessive for various reasons. So what subsequence does, it does not make a copy. It just basically gives you back a reference to the thing. So when you make a substring, the contents are still there, and you just get back a little header that keeps track of the fact that you have a duplicate header that's pointing to the same string. And if you have big strings, like we have here, like an entire work of Shakespeare, that's more efficient. And you'll see how that plays out later as well. So subsequence avoids copying. And I've got a really cool little class called SharedString that uses subsequence in order to do this optimization that I'm talking about here. We then have our list of phrases. We turn that into a sequential stream. And then for every phrase, we go ahead and we look up using search for phrase, which we'll come back and look at later. And we say, I want to see if that phrase occurs in this input string from this play with this title. And the false flag here means, and I don't want this to go in parallel. I want it to be done sequentially. Later, when we do the parallel version, you'll see that all we do is change the false to true, and boom, it goes a lot faster. So this takes in a list of phrases, or a stream of phrases. We get back from this basically, you get back from map the search result object that comes back from search for phrase, and then we call filter to get rid of anything that's empty. So anything that's empty gets thrown away. So we only have non-empty search results. And notice, by the way, that this version uses the method reference implementation of this. So it uses a method reference and a negator predicate. If we didn't want to use that for whatever reason, we could have written it like this. We could have said filter result arrow result.size greater than 0. So that has the same effect as this. It's just that I like the method references a little more. It doesn't really matter for something this simple, but this is just ever so much cleaner than that. You have to kind of stop and look at that a little bit more carefully, whereas this you just go, oh, this is letting through anything that's not empty, right? You can just almost read it left to right. These are both intermediate operations. They don't do anything until we hit collect, and collect starts the wheels in motion, does the processing, and then yields a result, which is a list of search results, which gets returned as the result of this method, and that comes back as a list of search results, and then that comes back over to the processStream method, and so we end up with a list of search results for the things that were not empty. Okay, so that's basically how that works.